This work was on efficient global point cloud alignment using Bayesian nonparametric mixtures. I'm Trevor Campbell. This is joint work with Julian Straub, Jonathan Howe, and John Fisher. In the 3D point cloud alignment problem, we have two scans of the same object taken from different viewpoints, and we want to find an unknown rotation and translation that aligns them. There are two major classes of solution to this problem. Local methods take small incremental steps in joint rotation translation space to improve some objective. These methods tend to be computationally cheap, but they're susceptible to the local optima that are typical of alignment problems. Another class of methods, global methods, search the whole space to find a global optimum in some cost function. These methods tend to have complexity that scales exponentially in the dimension of the space, and since rigid transformation space is six-dimensional, these methods tend to be slow. We propose a method for reducing the cost of global point cloud alignment significantly by decoupling rotational and translational alignment using surface normals. In the rotational alignment step, we first compute the surface normals for our 2 point clouds. This creates two sets of directional data plotted on a unit sphere here. We create parsimonious representations of these directional data sets using Bayesian nonparametric von Mises-Fisher mixtures. We then align the two posterior density estimates by minimizing their L2 difference using branch and bound, and this creates two rotationally aligned point clouds. In the translational alignment step, we start with our two rotationally aligned point clouds. We again create another parsimonious representation of them using Bayesian nonparametric Gaussian mixtures. We again align the posterior density estimates by minimizing their L2 difference using branch and bound, and this completes the alignment. Our work relies on our novel refinable tessellation of rotation space. We treat rotations as quaternions, which lie on the upper half sphere in 4 dimensions. As a 3-dimensional analogy, we start with the 20-sided icosahedron, which tessellates the sphere with triangles. And when we refine our tessellation, we split each triangle into 4 subtriangles, as shown here and then here. Now this tessellation is nearly uniform, having almost equilateral triangles. Now, of course, we're actually working in 4 dimensions. So in 4 dimensions, we start with the 600 cell, which tessellates the 4-dimensional sphere with tetrahedra. And when we refine our tessellation, each tetrahedron splits into 8. This tessellation is similarly uniform to the 3-dimensional analog, and the reduction in distortion of our tessellation compared to past work leads to more efficient exploration and global optimization. The resulting algorithm is robust to problems with real point cloud data like partial overlap, noise, and outliers. We use our algorithm to align multiple partial views of the Stanford Happy Buddha data set taken from different rotations and translations. This is a very challenging problem. No past global alignment algorithm was able to reconstruct the statue from these partial views. In contrast, our algorithm was actually able to stitch together the scans more or less correctly. We also used our algorithm to successfully align the Stanford Bunny data set corrupted with 60% outliers, and also scans of a cluttered indoor office environment. Our quantitative experiments on the apartment dataset show that the algorithm is both as fast as the fastest previously available global alignment algorithm and as accurate as the best previously available alignment algorithm. And that is all. Thank you very much.